forget to do that. Okay, and then I'm gonna hit share screen. Go to here.
Oh, I did have a question about our lecture summaries. Should we
Yeah.
try to definitely edit them down so they're exactly like 1 to 2 lines per lecture, or like how much of a general guideline is that versus?
Well, I'll tell you, I don't really know what Professor Eager's desires are, policies on this, but I know what his philosophy is on it, and I think it goes something like this: is that he believes that in any given lecture, there's only so much that you're really gonna find important, and therefore there's only so much you should really worry about remembering. So whatever it takes in order to feel like you've written down what you really think you need to know from that lecture, whether it's 1 line or 1,000 lines, whatever you're passionate about, I'm sure he'll be okay with it. So that's what I would say. How many lines do you think you're writing per lecture?
I mean, usually like 2 or 3. It's just some of them. So like the strengthening mechanism lecture, for example, because there were so many different types,
Right.
like having a note about like what each one was makes it a bit bigger. But
Okay, well, but if that's what it takes, that's okay. I think ultimately this is something that I think would be really good to like carry with you, outside of university and everything, wherever if you decide to go into academia or industry or government, just that you get in the habit of when you're out of a meeting, you just sit down for a couple minutes and you just say, okay, what did I really learn today? And then you write it out, and that way it really sort of, at least for the way my head works, it would really stick in there. Like I would remember it for years, what was the importance of that particular lecture. So whatever it takes to accomplish that.
Yeah, Robin, I don't know if you saw, but there was some additional guidance in the syllabus about like whatever it is that you submit shouldn't be more than 3 pages, which makes it down to, like, for a double module like this, 1 page, if that helps refine.
I mean, that's kind of what I was asking, especially for me. I like organizing things in bullet points and sub bullet points, but that also like expands the technical length because you're not taking up the full page for each bit. So
That's right.
He's not going to bark at you, don't worry.
Yeah.
And if he does, just tell me and I'll say, it was okay. blame it on me. So Sophia and Ryan, did you guys get the email I sent out yesterday about lecturing from Zoom rather than in the classroom?
Yes.
Okay, I'm really sorry about this. My wife's in the hospital today, and I had to get the kids off to school, and I wasn't really sure, like, well, I sort of knew, like, by the time I got them on the bus, I knew that I would not make it to Cambridge in time to be in building 4. So
yeah, no worries at all.
But I should be back at our next lecture, which I think is not next week, but maybe the week after. I think there's a holiday next week. Is that right?
Yeah, on Thursday.
Okay.
So the systemic part of it, I think, is done.
What, Ryan?
Oh, sorry. I didn't say anything.
Oh, I thought you did. I thought that was you. Sorry, because your microphone went on the second the person finished talking.
Oh, that was me. I said it was Veterans Day. It's a holiday.
Okay, Veterans Day. All right, well, good. Okay, so we have a fun lecture today. Might as well get started. And because I'm not in the classroom today, if anyone wants to go over this sometime outside of class, I'm happy to meet you guys anywhere at MIT, and we can talk about it. And, again, I can bring in some of the 3D models and things if you want to have a closer look. So here's I think the most important, or one of the most important topics we talked about last week, and that's sort of the idea of what happens when you combine finite element analysis with numerical optimization algorithms, and how can you use that to your advantage? And the answer there, of course, is that you can have a multi-dimensional design space, and then you can iterate through different designs within that hyperspace of variables and come up with optimal designs that are either light or strong or stiff or whatever it is that your whatever it is your design requires. And I talked about this paper here from Benzoa and Kikuchi, and this is one of my favorite papers. If you are interested more in topology optimization, it's a lot of fun. I suggest you go to the library and download this, or this. Obviously, you don't have to go to the library anymore. Sorry, go to the library website and download this. It's a great paper. And their strategy was this. They said that suppose you had this design space, packaging volume where you could put structure in, and then you discretize that down into finite elements, and then you choose as the design variable for each of those elements a density, and then the design space is varying through different combinations of different densities for each of those elements. And then by taking the aggregate strain energy of all those elements, once you've applied the boundary conditions, finding the place where the combination of different densities for all the different elements in your design space gives you a minimum. That's the point where you have the most structurally efficient load pass through that load volume, given those boundary conditions. Robin, you got a question?
So do you choose whether you're optimizing for strength or stiffness, or is it always stiffness?
In this case, you are optimizing for load path. So you're optimizing for minimizing the strain energy. Your objective function is strain energy, the aggregate strain energy of all these little elements added up together. And then once you've determined that, once you've found those, those elements, those combination of places where you have high density, if you were to design a structure and then consider putting the load beams along those places where the optimizer distributed density within the packaging volume, that's a place where you'll have the most efficient design. So I'd say the stiffest at the least weight. Okay, so it's really designed. It's really I guess maybe it is designed for stiffness at the end of the day. I'd have to think about that. But anyway, so we talked about this, and then we gave this little example here where we had 500 elements in this cantilever beam, and we pointed out that this can be very readily scaled up into millions of elements, assuming you've got a powerful enough computer. And here's an example of a project I did when I was an engineer at Chrysler, and we did a lightweight body structure for a big SUV, and we found the most efficient load pass through that potential packaging volume for an SUV, and we actually eventually converted that into sheet metal, but we identified the most efficient load pass using topology optimization, and this was scaling up to 2.3 million elements. So there's 2.3 million elements, and each one of them can have a density between 0 and 1. And then you have so much mass, and and you say, okay, I'm going to distribute my mass, or I'm going to distribute my density to each of these elements, and then I'm going to find out, okay, what's the best place to distribute them that gives me the lowest aggregate strain energy, and that's the most efficient design. And we talked about packaging volumes. The packaging volume can be anywhere where you can put structure that doesn't violate, like something like, you can't have a structural member through somebody's head or through an engine or a transmission. You might be able to use a transmission or the engine as a structural member, but you couldn't like put a load path like perpendicular and through it. And you have to hollow out for things like the motion of the wheels and places to put engines and sunroofs and things like this. We talked about different loading conditions that you put on a body structure: the front impact, rear impact, bending, torsion. We mentioned that these are sort of approximations of real world loading conditions, and the quality of your results will depend deeply on how well you figure this part out. How do you simulate the different types of loading? So one great example of that is impact. Like impact is a short duration, high energy loading event. And how do you simulate that with something that looks like a static load? And the first approximation that we used was just to distribute the loads over the front and rear bumpers to simulate front and rear impact respectively. But since then, I'm certain that the community has come up with better ways of simulating impact. For example, I know that some of my former colleagues are using the process where they sort of use time steps, and they apply the load and they deform, then they reapply the load and they deform, and they keep going until they feel like they've crushed to a reasonable point, like down to the firewall between the engine and the passenger compartment. And then the results look something like this. Okay, and this is the place where the optimizer has distributed the mass in this packaging volume for this SUV. It's pretty organic looking, actually. We talked about how there was this other method of calculating efficient load paths using another program called soft kill option. And the soft kill option mimics like tree growth, where it places mass where the stress is. That's kind of the way real trees work, and they're able to sense where they're stressed out. and put more wood cells there and start growing to take up that stress. The problem with something like this, of course, is that this is very complicated, and it's really, really difficult to take this type of organic looking structure and then convert it to something you can actually build. Say, car bodies are almost always made out of sheet metal. We did that by first drawing what we called a beam model. So we got about 6 engineers in a room with these results, and we just sort of hashed through it for about 4 hours, yelling at each other about where were the load paths and where were they not. And then we created these beam structures to create an abstract of this. So something more simple that could be potentially more likely manufactured. And the optimizers give you the option to look at cross sections as well, which include the original packaging volume, and then also include the places where the density is the highest. So this is like a topographic map of the color of density. So this is where the optimizer has placed the density in the structure. So you can see here these red areas, and these are the places that obviously this is the places where the density is actually equal to 1, and then the blue is where you're approaching 0, and these things in between are places where the densities are somewhat less, somewhere between 1 and 0, maybe around a half or third or 3/4. It's really interesting. This is a lot of fun to then go through these models, these topology optimization models, and then go through and see exactly where the optimizer has placed density. So again, this is, when you look at this result, this is where the density is above some threshold that you can typically set in the software. So you can tell the software, like, show me only places where the density is above 0.8, for example. And this is just another way of looking at that. Sometimes this is more helpful. And then here's another example. You see another cross section here where the optimizer has distributed density to minimize the aggregate strain energy. And then here's another cross section. You can flip the direction and start looking at cross sections that would be before after the car body, for example. This is this right here. This is a D segment vehicle. So this is like your Toyota Camry, or I don't know, Ford. What do they call that one now? The Edge, I think, or something like that. Honda Accord. This is that vehicle that would compete with that. But you can see here where the optimizers place density, and
That was still the front energy or the front impact load case, correct?
correct. This is an aggregate of the 6 different load cases, I think it was, that I showed on the previous page.
Okay.
We applied all of those simultaneously, and then did the, well, I take that back. In this result you're looking at right here, they were all applied simultaneously, but we did do them individually as well to understand what each loading case would do in terms of creating density maps. What I want to show you here is kind of interesting. If you look at the roof structure here, up here, the optimizer creates all these Ks and X structures. And from experiments we did after we converted this to sheet metal, we found that these K and X structures were extremely efficient in improving torsional rigidity of the car body. And yeah, it's interesting because there is no car on the road that has this. They're all like basically just cross members, straight lines. There's nothing out there that has Ks and X's, yet it's so incredibly efficient. There might be one Volvo out there, but we found that might have been an accident. We also did this method using individual components. So here is a shock tower. As I told you before, this is where the springs and shocks feed their load into the body structure. This is typically one of the highest stressed under normal driving conditions. This is perhaps one of the highest stressed areas in the car body. And you can focus on individual components like this and then do a topology optimization, a beam model, and then convert it to sheet metal. And you can see here on the far, I guess that's your far, that is your far right, just like mine right now, right? You can see what the final structure looked like. And this, I don't know if the structure ever went into production, but I sure pushed like hell to get it into production. This is supposed to go on a Chrysler Sebring at the end of the day. I don't think it actually did go into production, but normal shock towers today that you would see in a car don't have these cutouts, for example. Right? See this cutout right here? My cursor is over. That cutout can save, a couple grams maybe a kilogram in total. And so this is interesting. This takes weight out of the vehicle. It doesn't affect the stiffness or the strength or the fatigue resistance of the car. And you've got this opening that saves you some weight. So the problem is that in some vehicles, this means that you're getting a lot of junk, road grime and dirt and water entering the engine compartment, which isn't necessarily desirable. So
Acoustic noise would be another factor too, right?
acoustic noise, exactly. That's a good one, exactly. But you say, okay, can I cover this hole up with something that has a much lower density than steel? It doesn't have steel's mechanical capability. Can I cover this up and like save most of that weight and still not have the issue with acoustics or having some type of, road grime and water getting inside the engine compartment, causing problems? Water does get in the engine compartment, be sure, but it usually comes in from the front. So the entire body structure that you saw back a couple slides here, this one, the SUV, this was the result after we had converted that into real components, real sheet metal. So this was done by a group of about 4 CAD experts to turn our results into real sheet metal. Some of the load paths that we found that aren't, at least in the day, weren't typical in production vehicles, are like this sort of strap that goes from the front of the rocker panel up to the shock tower. Okay, so that was one load path. Again, that cut out in the shock tower. Back then, the load path that went from the shock tower to the cowl wasn't quite so popular. There was on some vehicles, but very few. The inside of the tunnel, there was sort of these web structures that we kept finding, and then the structure that would connect the rear shock tower to in this case, the C pillar. That's this one here. That's remember the A pillar was like where your head is. It's like where the rear view mirrors are. Then the one that was next to your shoulder was the B pillar. Then the next one back was the C pillar. And then if it's an SUV, then if it's an SUV, there's a D pillar behind that. So this is the C pillar on this SUV, and this little structural member right here was very effective at increasing torsional rigidity, and it's just something you don't see in real vehicles on the road. Then I've already mentioned the K structure, these K and X structures right here on the roof of this SUV. These are very, very efficient at improving torsional stiffness, but you don't see them on current cars. In the rear of the vehicle, or on the floor pan of the vehicle, there was many types of X's and K's as well that were turned into load paths. Actually, there's a paper out there on this if you guys are interested in reading it. It's SAE 2008010880. You can find this, I think, probably find this in the library. You can read some more about this if you're interested. After this exercise was complete, we decided to go out and start benchmarking vehicles to see if we found evidence that this topology optimization was being used anywhere on real vehicles that were driving around. And the management of Chrysler was very surprised to learn that, oh wow, it really is true that our competitors have been using this and probably been using it for a long time. So this is the bottom of a 2006 RAV4, and the topology optimization result on the top from our SUV, and you can really clearly see the congruency in the structural members here. You see these. So this is where so this would be the separation right here between the passenger compartment and the engine, like right where my cursor is going up and down. And like this would be the tunnel that's next to your legs, and the shift lever would be up here somewhere, and the rear seats would be back here. And you can see how the optimizer has taken this load that would be coming in from the front of the vehicle, bifurcated it out to the rocker panels right here and to the center tunnel. And you can see that how Toyota in this RAV4, they've done exactly the same thing. So here's right here would be, this is looking underneath the car, right here would be where the dash panel is. Your seat would be like right here. And then this is where the transmission goes. So the shift lever would be going up to that hole right there. And you can see, like, here's where the front rails come in and how they've taken that load and they've bifurcated it again to the sill structure and to the tunnel rails. So you see that. So there's a clear proof of the optimization results were used in a real production car. we found a lot more. Here's a Honda Accord, a 2000 Honda Accord. And a lot of the structures that we found in the front of the vehicle were very, very similar to what we saw in topology optimization results. When I presented the topology optimization results at there was a Great Designs in Steel show in Detroit in, what was that, would have been 2008, I think. We presented this, it's a Representative Chrysler, we presented this, and it was like, we found this, we did this, and we found out later, like the Honda engineers were laughing because they've been using it for like 2 decades or something, or a decade before we got into it. So this Honda Accord shows that they had been messing or playing with this topology optimization tool for quite a long time. Another example is this structure right here. This is the, if you open the trunk on a Honda Accord and you look right or left, we call this the quarter panel area. This structural member right here allows you to increase the I guess local frequency of the rear of the vehicle, as well as the torsional stiffness of the body structure. So here's another example. Then this is the rear wall. So that this is right in front of the rear seats. If you have skis or something, you would be passing them through here. Okay. And these are the structures that we found in topology optimization, again, generating these X structures. And we found some evidence in this Honda Accord that they were seeing, they had very similarly converted this to sheet metal. It's grab some water here, hang on. You can see these red, some of these parts are painted red, some are painted blue, and some are painted white. Can you guys see that? So what this was, this was, I think, at the 2008 LA Auto Show that we found this. And you can see these different colors. What these different colors corresponded to was different strength steel. So Honda, knowing the topology optimization results, had made the primary load paths out of more expensive high strength steel, and then made the places where they didn't need that much strength out of less expensive low carbon steel. Okay, so these white areas don't really take that much load in impact or torsion or bending, side impact. They don't really take up that much load. So there's no point in spending a lot of money to make those out of expensive high strength steel. But making these primary load paths, these red parts and the blue parts, that makes a lot of sense. You get some advantage for using your money there and some potential weight savings, because the material is stronger, you don't have to make it as thick, and therefore it can be lighter. Looking at this just now, I guess I realized that those diagonal members are probably there for rear impact. They're there to take the load from the rear bumper up into the C-pillars. And that's why Honda went ahead and used a high strength steel there. Any questions on this, guys? No? Here is this is a 2008 Audi A8. So this is the gigantic, four-door luxury sedan, the S-Class, S segment vehicle that Audi makes. And this is a vehicle that they have made out of aluminum for a long time. And this is the front end of it. And here's the results to some topology optimization on the right. And you can see so clearly here where they've taken these topology optimization results and they've made them into the front end of this body structure. So everything you're looking at here is aluminum. Here's the right shock tower. Here's the left shock tower. And then you can see how they've done their shock tower with these big spaces between the main structural members of the shock tower. And then they've triangulated the two shock towers between each other and to the what they call the cowl structure. That's this area right underneath the windshield where like the windshield wipers go. And then you can see the front rail structures here. Beautiful piece of engineering. What's interesting about it, though, is they don't seem to save that much weight by using into aluminum, which kind of always surprised me. If you look at the vehicles that compete with this, like an S-Class Mercedes or whatever the big Jaguar, well, that's a bad example, the S-Class Mercedes or the big BMW, the big 7 Series BMWs that compete with this Audi A8, those cars are all made out of steel and they're not that much heavier. So I always wondered, like, what was going on here? And I think the answer may come down to fatigue, and I'll talk about that in a future lecture. But aluminum unlike steel, doesn't have a fatigue limit. There's some combination of stress and number of cycles where an aluminum part is going to fail no matter how big it is. Steel, that's not the case. Steel, there's some combination of loads and cycles where it'll go on forever and you never have to worry about the part failing ever unless it corrodes away. Any questions on this one, guys? These guys, nothing? Okay, we're good. So in talking about load paths, what do you guys think that this Formula One car from the 60s here on the right and this tractor have in common? Someone want to venture a guess?
Both using the engine and the transmission as a load path.
Yeah, you probably read that up here, right?
Oh, I missed
Um,
that.
No, this fascinated me. So on the right here, this is the Lotus 49. This is considered a milestone Formula One car. And the reason it's important is because this is the first time that any Formula One manufacturer had ever used the engine as a stress member. So the stress member becomes the load path, right? I mean, it makes all the sense. You've got this big, gigantic block of aluminum, or maybe 3 or 4 blocks of aluminum, and they're big, stiff, and strong. And why would you put a structural member next to it and have all that redundant structure if you can just go ahead and use the engine as a structural member? And certainly, when I was at Chrysler, I was all excited by this, and wow, isn't this cool? Like, you can, what a genius Lotus is, and their founder Colin Chapman, that they came up with this idea of using the engine as a stress member. And then one day, after I moved to Boston in 2009? Yeah, 2009. I was at some ice cream stand up in Concord somewhere, and I came across this tractor here that you see. And I thought, oh my God, they weren't that smart. Someone had already done it, because here's this tractor where the engine and the transmission are the primary structure. The axles from the rear wheels and the front wheels pretty much bolt exactly straight up to the straight up to the engine here. And then so there's no, this is this old tractor from 1917 built by Ford. And you can see that the engine, the transmission is the primary load path. And they're double using those components. See that? So nothing's new, right? Everybody stands on the backs of giants. And even Colin Chapman from Lotus, he stood on the back of a giant too. Apparently it was Henry Ford. This tractor here, this has the engine used as a structural member. Some other clever things that actually Lotus did do, actually I should mention, is that, for example, like they use these tubular frames, and rather than having tubes, like flexible tubes to supply oil or to go to the oil and water coolers in the front of the vehicle, they went ahead and ran the oil through the structural members. So they could reduce the weight by not having those extra rubber tubes or stainless steel tubes or something that would go to the front of the vehicle to the radiator and exchange the heat and come back. So that's how you reduce weight. You use a component that already exists for multiple functions. That way you don't have to create a second structure that just adds weight. This Ducati here, this is my friend's Ducati, lives in Berlin. And you can see here on the right is the motorcycle on the left with the bodywork taken off, and you can see the engine right there. It's right here. There's 2 cylinder banks. There's this one going up, and there's this one going fore aft. And this sort of gray tubular structure right here, this is the structure that connects the forks to the engine. So the engine, and then the structure right here that connects the seat structure basically to the engine, and then the rear suspension basically bolts directly into the transmission, which is right about here. So in this case, as you drive down the road, the engine is actually under bending. And this is a way that Ducati is able to reduce weight, because they don't have to put structural members that would go underneath the engine, like down where my cursor is going. And then those would be probably in tensile load, right? Because they go underneath the engine, and this thing, the bending load is down, you know, where my cursor is. And so this is pretty clever. This is a way Ducati is able to minimize the weight of this motorcycle without sacrificing much stiffness. You may ask, does anybody do this on a car, a production car? So the problem with this technique is that it is not pleasant from a vibration perspective. We call this noise, vibration, and harshness. When you have an engine firing and the engine isn't perfectly balanced, there's all kinds of vibrations that come up. And if you buy a Ducati, you're kind of waiting for that, so it doesn't bother you. You just expect it. But for most customers who aren't fringe lunatics, seriously, that probably wasn't very nice. Sorry. For most customers who aren't Ducati racing enthusiasts, the amount of vibration, would just be completely unacceptable. And here's a Ferrari. This is, I think, one of 2 cars they ever tried this on, where they used the engine as a structural member on a passenger car. This is the Ferrari F50 that was made in the mid 90s. And I think this is the only Ferrari supercar that wasn't successful, that I think actually loses value with time, not gains value. It has a gigantic V12 engine that was directly bolted to the structural member behind the passenger compartment here, behind the front seat. This isn't any rear seats. That's the structure here. So here's the engine. There's some auxiliary, struts here going back to the transmission, but this engine is hard bolted to the chassis. And a lot of people who buy these cars probably weren't too happy with the amount of vibration that the engine was kicking up. And when they replaced this car with the Enzo in the mid 2000s, it was the mid 2000s. I think it was early 2000s. I take that back. They didn't do this again. They didn't use the engine as a structural member. So in a four-wheel vehicle, using an engine as a structural member, I think is really only confined to racing cars. Although it is definitely a way to improve weight. However, here's where things get cool. The electric vehicle may enable that concept to come back, because when you have an electric vehicle, you don't have the vibration because there's not a bunch of burning gasoline in there. So here's a scooter that I think is really interesting that BMW made in 2018. It's an electric scooter, and you can see it on the right here with the bodywork removed. And this center casting here, this is actually the battery box. This is filled up with lithium-ion battery cells. And the suspension, the rear suspension bolts, or the motor, I should say, bolts directly to that structure. The motor's back here. And then this structure that supports the forks, that bolts directly to the top of the battery housing. Okay, putting this battery housing in bending. And the lithium-ion battery cells, like, I don't think they really care that much. I mean, they can, there's a little bit of stress there. I think they're okay. But this also contains the inverter and the control unit. The inverter is the device that converts the DC signal of the lithium-ion batteries to AC, so the electric motor can use it to turn its armature. But this is really clever, I think, and this really excites me. And back when I was at Chrysler and people were sticking their nose up over electric vehicles, I kept saying, this is back in 2008, and we were aware that Tesla was trying to develop an electric car, and we all kind of said, "Oh, that's impossible. That'll never work. No one will buy it." We were pretty wrong, obviously. But anyway, and I kept saying, "No, you guys are wrong. I mean, look at the opportunity here to reduce weight, because you can use some of these things that are heavy, like battery boxes and structural members." And I think that's exactly what Tesla does. I think on the Model 3. Correct me if I'm wrong, anybody, but from what I understand, they use the battery box as primary structure. And they do that as well, I believe, on the model, is it the X or the Y that just came out, the smaller SUV. So this is something that's already moving forward. I don't know of anyone who's actually put the for example, the motor housing in stress or under load, but certainly the battery boxes, they're a prime candidate to be put in load. And as I showed you, I think in a previous lecture, like Elon Musk is even talking about using the individual battery little coils, the little cylinders, using those as structure too. So pretty cool stuff. There's opportunities in electric vehicles that we don't have in gasoline powered cars to reduce weight. Robin.
So I think there is a lab at MIT that was looking into this, and then one of the main people moved to Temple semi-recently, specifically about like FEA modeling and strength modeling of battery cells,
Really?
and kind of how they react to impact too, because now they're in the load path.
When you say they went to Temple, you mean Temple University?
Yep.
Huh.
Like one of the main research scientists who is working on it is now working on it at Temple rather than MIT at this point.
If you happen to come across that person's name, I'd love to have it.
I'll look
Really
it back
curious
up.
to see. I'd really be curious to see what they're up to. But this is a tremendous opportunity to reduce weight, to build more efficient structures. I'm really excited about this.
Just had a light bulb moment on why Tesla is casting their shock towers. If their car is so much heavier, right, and the shock tower is, a stress limiting member.
It's interesting. The shock towers are really on the limit oftentimes. When we launched the Chrysler 300, and the Charger and the Magnum in 2000, what is it, 2004, 2005, 2006. The early prototype vehicles were destroying the shock towers in endurance testing. And we ended up putting these huge plates on top of the shock towers to take up the load. About that same time, or maybe 2 years after that, BMW introduced in the 5 Series of that, whatever, mid 2000s 5 Series. They introduced a vehicle with aluminum shock towers. And we were all surprised by it because we thought that, they're aluminum doesn't have a fatigue limit. How does this work? And I guess there's enough mass there, there's enough cross section, they can get the stress low enough that they get enough cycles out of it, they're content. I don't know what that number is, but they're apparently like, okay, this is good enough. And then the advantage of it is that you have more, I think you've got more geometric freedom to mimic the topology optimization results, And then the other thing about it is that you're using fewer parts. And that's really the motivation why Tesla is using these huge cast parts, is because they want to reduce the part count. It makes all the sense in the world. I mean, you have, for each part, you have to keep track of the number and how many you got in the factory, how many you ordered from the supplier. And there's people working on that. So there's real money involved. There's real money involved with doing that. Oh, thanks, Robin. That's okay. Got the link here. Thank you. Anyway, there's real money in that, right? So it makes sense to reduce the number of part count, number of parts in a given assembly, and then the whole thing about having all these parts in the factory and the real estate that those parts take up in the factory, and making sure the parts get to the assembly line on time, and it's a nightmare. It's an absolute nightmare. So it makes all the sense in the world to minimize part count. And I think to some extent, some of the car manufacturers are really jumping for joy over electric vehicles because there's fewer parts, right? Internal combustion engines are incredibly complex. They've got a zillion little pieces in there, right? And a lot of them have to be very carefully machined and X-ray to make sure there's no cracks in them. And it's just too much money. Electric motors and batteries are far simpler. Okay, come on. There we go. Okay, so I've shown you how finite element analysis and numerical optimization can be linked together to create this tool that helps you find the most efficient load path through a given packaging volume given a certain set of boundary conditions. And this is one tool that method, or those two subtools, have come together to help us lightweight structures. So here is a graph that describes a couple different methods of how you use these combinations of numerical optimization and finite element analysis to come up with ways of reducing weight. Another tool is called topometry optimization. So there's topography. This next one is topometry. Topometry optimization is using these tools to determine what is the optimum thickness for each panel in a sheet metal body structure, or sheet metal any component. But in this case, I'm showing a body structure. So the way this works is that the design variable is the thickness of each of the sheets. So I can tell you that in a Chrysler product, there may be 300 or 400 sheet metal stampings in a body structure. Mercedes, there might be 600 stampings in a body structure because they're just, it's all about that complexity. So if you've got that many panels and your loading conditions, you can use a numerical optimization tool combined with finite element analysis to determine what's the optimum thickness for each of those panels. And so that's the design variable. Your design space is 300, and each of those 300 is a thickness. And then your numerical optimization will iterate through those different thicknesses and do finite element calculation for each thickness and come up with which combination of thicknesses gives you the stiffest structure. In practice, this tool is used very similar to the way topology is used, in that it calculates out an aggregate strain energy for the whole system. It doesn't calculate out minimize stress or maximize stiffness. It actually does strain energy, which of course turns into optimized stiffness. Another tool is called topography optimization, and this is optimizing the topography of a stamped part. So if you've ever looked in some of the parts of your car body, like every panel on a good car oftentimes has all these little tiny beads and little little indents and little things sticking out, little structures of little ribs that come together. And these are there to increase the stiffness. So if you just take a flat panel, right, obviously the stiffness is blah, next to zero, right? If you load it in the off plane direction, right? This comes back to that section, that polar moment of inertia, the blah 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 over b cubed. So finding the correct topography of the structure oftentimes comes down to finding certain resonant frequencies and vibration modes. So honestly, when it comes to designing cars, passenger cars that you guys drive down the road, probably so much effort is spent on reducing the amount of vibration and noise that the car makes when you're sitting inside it. So as you're driving down the road, you hit certain frequencies. There's like certain road inputs, like maybe there's a washboard, like the road has like ripples or something in it, or there's those little things on the side of the freeway to wake you up when you fall asleep. Hopefully not, but I'm talking about. Hopefully it wakes you up. Hopefully you don't fall asleep in the car. But anyway, then there's inputs from the engine. The engine's turning, it's making a vibration, and there's this huge game that the car industries have to play where they have to make sure that none of those frequencies coincide with the natural frequencies of structures of the body or suspension components or even transmission housings or engine blocks, because you don't want those two to hit a common frequency and then have a resonance, which would make the car uncomfortable for a driver. So a lot of times these bead and rib structures are engineered to change the natural frequency of the part or change local frequencies within the part, so that they never hit a frequency that coincides with the road input. So this tool uses what are called displacement or perturbation vectors. And what that is that you have like the original part, let's say, that's basically just flat. And then you put what are called perturbation vectors all over the part at the nodes between the finite elements. Okay, and then the design variable becomes how much do you displace the design vector, this perturbation vector, and each of those corresponds to a deformation in the sheet material, right? So you do a grid of these perturbation vectors. So suppose you put 500 perturbation vectors down, and you've got a 500 component design space. Okay, and the optimizer goes through and it determines, if I displace the perturbation vector by this, which is displacing the surface, how does that change, say, the natural frequency or the aggregate strain energy of the part? And that's the optimization. The finite element analysis happens after each change in the perturbation vectors. Okay, the perturbation vectors, and then the optimizer iterates through different designs of different amounts of perturbation, different amounts of displacing the surface of the sheet metal part. And that's what can create these bead structures. A similar technique is used in what's called shape optimization. And this is, for example, if you have a beam and bending, right? The square cross section isn't always the most efficient shape. Like you guys have probably seen like I-beams they use on buildings, and Robin, I'm sure you have. And so those I-beams are, that's a design where you're putting material where you need it, above and below the neutral axis of bending. Okay, and so this is something that I-beams for buildings and things that was probably figured out over years of people thinking about it. But sometimes the loading cases are too complex and you can't just figure it out so intuitively. And that's where these shape optimizers come in play. And this works very similar to topography optimization. You have a cross section of a structural member, like you see here, for example, and then you apply these perturbation vectors to the surface. And then as you iterate, you're moving the surface up, in, or out, or whatever direction that's consistent with the perturbation vector, and then redoing the finite element calculation to recalculate out the aggregate strain energy and determine what's going to be the stiffest part. And then you keep operating until you keep iterating until you come to some type of point of convergence where the changes don't change. When the perturbation vectors are moved a tiny little bit, you don't get a big change in strain energy. This is used in rocker panels, rail structures on cars, It's also used very much in bicycles. And I'll talk about that one in a second. The final optimization tool I want to talk about here is called fiber ply orientation. This is specific to composite materials where you have a laminate structure. And as any of you guys know who've ever played with composites or taken a course in this, the whole game is what angle do you put the ply in? Okay, so you have a unidirectional ply of carbon fibers and you're stacking up a laminate. What direction, what angle with respect to the other fibers do you turn the fibers of the additional ply to in order to get the stiffness or the strength that you need? And the angle of a ply can be a design variable. So just with the other tools, you can put a laminate together and then apply like a rotation vector to each of these different plies. And then the design space becomes how many different angles do you have? So how many different plies do you have effectively? And then an optimizer can choose one set of angles, do a finite element calculation, determine an aggregate strand energy level, turn them again, then calculate and do a finite element analysis, and then determine the strain energy there once you've rotated it again, and over and over and over. So, long ago, several weeks ago, we did these very simple cases where we had these two-dimensional design spaces, right? And we looked at these different struts and columns and things, right? And we just basically found the point within that very simple two-dimensional design space, right? Of where's the most effective place, what's the most efficient place to put these, to make the thickness or the length or the cross section or the diameter of these different little tubes and things. And that was a very simple stress calculation. It was a very simple design space, and this is something that all of us were able to do right there, kind of looking at it in our head. It wasn't that complicated, but the advent or the ever decreasing cost of cheap computer processing power and memory enables far more fantastic and complex things to become possible that can't be done intuitively because our brains just aren't powerful enough to do it. But I hope you guys can see, I hope you can draw the connection of these tools that I'm showing you here and that very simple two-dimensional design space. So this is really just the same exact thing, but it's been bumped up several levels of complexity enabled by high-powered computers, cheap high-powered computers. Make sense, guys? Ryan's shaking his head. Sam's shaking his head. This is really neat stuff. I bet, Rob, I guess, I understand, in the presentation that you gave with the performing platforms and things like that, I don't know how interested they are in light weighting, but they're certainly interested in cost, I bet.
Light weighting is a huge deal because you're limited
okay.
by the number of motors you have.
Okay.
So like the number of motors you have, you can't go over that because if you go over that number, the thing won't move.
Okay.
And everything is as big as possible, as ridiculous as possible. So if they can not get more motors, but have it be bigger and hold more people.
Right. Kanye West wants something the size of a football stadium, I'm sure.
But your timeline is like months. So optimization tools aren't necessarily going to be used.
Oh, wait a second. No, I would disagree with that. These tools save you time. For sure, they save you time. They're much quicker than iterating.
There's no iterating.
But that's the thing. Like if you're at some point where, okay, we're just going to be happy with this thing weighing 5 zillion tons and that's okay, when you might be able to give Kanye a bigger stage, or maybe you're going to make a better snake for what's your name to walk up, Taylor Swift. I don't know. I think you could be a real star with this tool in that field. Seriously, like I could totally see these tools being used to optimize the stress structures, like the diameter of the tubes, the wall thickness, all those things holding up the platform. I don't know. I think there's something here. I think this would be a really good application for that. And I bet it could be done much quicker than you think.
It might be good for theme parks, or for like the cruise ships, the cruise ship shows for sure.
Okay.
With touring, it's very quick slapdash. We've already ordered all of the tubes before the design is even started, because if we don't, they won't be here in time.
Okay. Well, if you ever can get ahead, think about this. Give me a call sometime if you go back in that industry. I'd love to take a look at it. Okay. So I think we're out of time here. We should probably stop, but I have some examples here of the application of some of these tools that we used at Chrysler and how we came up with, like in this case, different rib structures for a rear wheel house. That's the metal structure that goes over the wheel in the rear of the car. Here's another example where we use the topometry optimization on the various pieces that shingle together to make up the ring that goes around the rear lift gate on an SUV, and how we were able to reduce weight. And talk to you about these two bicycle frames I have here that show how each and every tube along every cross section has been optimized to maximize stiffness with the least amount of weight. This is really, these bicycles are incredibly lightweight and incredibly stiff. And I think this is a great example of where these tools have been used with great effectiveness. Anyway, we'll get into this stuff next week. Or not next week. When is our next lecture? The week after next? I think the 11th is our next lecture. And I think that's a holiday. So it's the week after that.
I don't think he put one on the schedule.
It looks like the 11th is a holiday. So it must be the week after that is our next lecture.
Yeah, the 18th.
The 18th, yeah.
Is that going to be our last, or are we going on to the 25th too?
I thought there was one more in December, or maybe even two more in December. I'll find out.
Okay.
I hope there are, because I still have a couple things I want to show you guys.
Great.
A lot of stuff I want to show you. Okay. All right. Good. Anyone have any questions or anything? Robin?
Maybe one day I'll tell you my horror stories about having to do composite repair on V22s. They
You know,
have,
composite repair seems like a really bad idea to me, quite
Yeah.
honestly.
they have drastically varying layer orientations, and they use very unique single direction cloth.
Right. You have to
Uh,
use, that's the way to really get the efficiency out of
I mean, typically like,
composite.
you see a lot of cloth, like interweaved cloth used, and then you could just orient every 45. But when it's a single direction, each ply has a very unique orientation that has to go in.
So the problem with the woven material is that you've got the kinks in the fiber, which intrinsically reduce the stiffness, right? You want to use those fibers when they're straight. That's how you get the real, these bicycles, these are not woven. These are all these unidirectional plies. Like some of these things have 600 little plies that are put together by some poor guy in Taiwan with, a pair of gloves on, just laying things up. It's really must be miserable, but they do a great job of it. And I do mean Taiwan. That's where most of these things are made. Okay, good. I'll see you guys next week. Bye.